Okay, looking over your exams that were returned, just a quick comment on the scores. There are several different numbers that are listed just so you are aware of what each of the numbers represent. First of all, there's a score out of 48 points. That is the score that you received on the multiple choice portion of the exam. That score was achieved by taking the number of questions you had right on the multiple choice on the Scantron, multiplying it by 3, and representing that score out of 48 points. The score out of 52 points is the number of questions you got right on the handwritten portion of the exam. To achieve that number out of 52, I took the number that's at the lower left-hand corner of your front page. If that number is a 6, I took that 6, I subtracted it from 52, and that would have listed as 46 out of 52. That number in the lower right-hand corner of the front page is the total number you got wrong on the handwritten portion. And then I got that by summing together the little numbers at the bottoms of pages 3 and 4, which are the 2 hand-graded pages. I do this all in my head. I do it very fast. In fact, I discovered that somehow I forgot to save the final version of your exam. On the final version of your exam, it should have added up to be 100 points. In your case, it was 99 points. So basically gave you a point for putting your name on your exam, since it did not add up to be 100. And so on my final version, apparently it was on my computer, that was not the one that I printed. Apparently though, I was lucky enough that I printed an exam without any other errors in it, because there were other errors that I had corrected, but I must have just forgotten the final save with the correct number of points. Then there's a score that is shown as a +3. That is just what I call a correction factor. You might call it curving or whatever. You know, I don't do that very often, but sometimes if the average is a little bit lower than I like for it to be, I'll add on the value of a multiple choice question. So that is basically everybody just got 1 free miss on a question, and that's where that 3 points comes from. So in the end then, you should, whatever score is circled on the bottom is a score that wound up going into the D2L white space grade book. Any questions on those grades? All right. I don't want you coming up here during the class, so at the end of class, if you came in late, you will find your exam up in these folders. You can pick your exam up at the end of the hour here today. They are sorted by last name. Okay, just a quick reminder here. We do have a review that's scheduled for this class period on Thursday in here. So we'll review in here at that time, and basically any questions that you have, we'll answer. We do have a review guide for the final that we passed out in here on last Thursday. If you were gone on Thursday, anybody need a copy of the handouts from Thursday? Okay. So there was a review guide and some questions we went through. And let's see, we did talk about the fact that only non-programmable calculators are allowed. I surveyed the class. There were 13 of you that said you did not have access to a non-programmable calculator. So I will have those calculators for you. If you didn't raise your hand, that means that I expect that you will have a non-programmable calculator with you for the final, because I only pulled aside enough calculators for us to use for that exam for those that didn't have them. My availability next week shown here. So go ahead and check out hours that work with you. I will be here many hours beyond this. That is, if I am in my office, you should always feel free to stop by. But these are the times for sure that I will be in my office during final exams week. Other than that, let's see. I did post to D2L Brightspace a list of study sessions, which I thought that I had put up here for your class, and I didn't. So I think I put them up here for the morning class that I just finished teaching. They have 10:20 scheduled for us. There are study sessions that are scheduled for today at 2 o'clock. It looks like Friday at 9 a.m. And these are down in the Academic Support Center. These are more structured review sessions. Have any of you ever gone to review sessions here for any class before for finals? Okay. So if you've been there, usually they have like some sort of study guide or packet and questions and the professional tutor. And if there's some peer tutors down there, lead those sessions. Basically go through the review packet and you work together. And students from all sections of 1061 will be invited, not just your class, but from all of the sections of 1061. You can feel free to go to none of them, to one of them, or to both of them. It's your choice. These are when they're available. Any questions? Yes?
Will we be able to just go and get a packet if we can't make those times?
It's probably likely that you will, but that's something that you can visit the Academic Support Center. But, okay, anybody else? And those are this week. And again, the first one is today. So any questions you have? Okay, we had a packet that we passed out in here about a week or so ago. And a week or so ago, it would have been a table of electronegativities. I wonder if I didn't put that on the wrong one. I bet this is where it is, yeah. So if you have that available, you can pull out that packet with the electronegativities on it. I'm going to move this here from Thursday. We'll cut that and we'll put this on today's notes, which is right here. There we go. This here is a table of electronegativities, and we've already defined it on here, but just in case we've forgotten what they are, we could talk about the electronegativity as being a relative measure of the attraction an atom places on shared electrons. So it's a relative measure of the attraction an atom places on shared electrons. And for our last exam, you were already expected to know what those trends are. You may remember that as we look at the trends, in general, as you go across from left to right on the periodic table, the electronegativity values will increase. And as we go down within a group, the values tend to decrease as a general rule. There may be some exceptions, but again, as a general rule, that's what we would expect to find. Now, what we're going to do with this here today is we're going to talk about polarity as it pertains to both bonds and molecules. And when we talk about a polar bond, we define a polar bond like this. We define it as being one in which the electrons are not shared equally. Whereas a nonpolar bond, which your text also refers to as a pure covalent bond, we said in these cases that the electrons are shared equally. And we get these simply based on the values of the electronegativities. So when we look at the electronegativity values, if the electronegativity values are equal to each other, say like we had an atom of nitrogen bonded to chlorine, these two have electronegativities are equal, we would say that that type of bond is a non-polar bond. That means that because they're shared equally, there's no real poles associated with them. But if they're different, for example, if we had a oxygen atom bonded to a, I guess we could say even oxygen to chlorine. If these two bond to each other, this type of bond is going to be a polar bond because those electronegativities are not equal to each other. And the shared electrons always spend more time with the one that has the greater electronegativity. So again, as you look at these values, the larger the electronegativity, the greater its attraction for shared electrons. Question?
Or just I'm saying in the mastering chemistry, they said where like if the difference between the electronegativity is less than 1.8, that counts as non-polar.
Not if it's less than 1.8, it's if it's less than 0.4. So I don't really worry too much about that distinction. It should be very clear. Of course, you're not seeing any tests from me on this. If you go into your next semester, I can't speak for who will be teaching your next course in the sequence, but usually we try to make it very clear to you. If they're equal to each other, it's nonpolar. If they're not equal to each other, it is polar. But your text will use a guideline that says, well, if it's close to 0, which means if it's less than 0.4, we still typically call that a nonpolar bond. But I'm pretty sure that your A6 exam will make it very clear. It's not going to try to trick you into, oh boy, it's 0.4. Is this polar or nonpolar? It's going to be very clear. They're going to either be equal to each other or they aren't going to be equal to each other. Okay? Anybody else? Yeah. Okay, and remember that the larger the electronegativity values, the greater the attraction for shared electrons. Now it turns out that the polarity of bonds is something that most of you are going to get just fine. Where most of you are going to have your trouble is determining the polarity of the molecules. But this is actually where it's more important. And so we are going to look at the distinction between a polar molecule and a non-polar molecule. A polar molecule and a non-polar molecule. And polar molecules have what we say, they have what's called a dipole moment. And a moment you can kind of think of as being a physics term. You might talk about the moment of inertia. We're not talking about inertia here, but we're talking about the fact that if a molecule is polar, it's something that we can measure, and we say that they have a dipole moment. And if the molecules are nonpolar, what we say is that they have no dipole moment, or their dipole moment is equal to 0. And they are not going to have any sort of attraction for a electrostatic field. So sometimes, not only do we say that they have a dipole moment, but we also say that their dipole moment is non-zero. So by saying it is a non-zero dipole moment, what we're trying to say is that it does have a value for the dipole moment. Now to do this, I'm going to bring out the kits we had the other day. And if anybody wants to follow along with the kit, I have 4 kits with pieces already built. Does anybody care to have one here today? Okay. Anybody else? And let's try to leave the pieces together that I've already pre-built for you. And I know it's fun to try to want to play with these, but if you could avoid playing marbles or whatever here today. I do want to show some examples of how we determine molecular polarity. And again, these are ones that are best looked at by examining the molecules in 3 dimensions. And we're going to start by looking at something like NCl3. NCl3. Now, if we were to draw a structure of NCl3, if you have the kits, what we're going to do is we're first going to build the Lewis diagram. And so we'd build the Lewis diagram by counting up the valence electrons. Nitrogen, of course, has 5. Chlorine has 7. And since we have 3 chlorines altogether, we're going to have 26 valence electrons. Well, now if you start building this model, you're going to see it's going to wind up looking something like this. And I'm going to show the chlorine here on the plane. And we're going to show the one that gets projected outward here, and then the one that gets projected back into the board. So if you were to build this model, what we're going to do to build it is you take and count the total number of electron groups around this nitrogen atom. And so how many nitrogen groups, or how many electron groups are there around this nitrogen? There's 4. One of them is a lone pair, the other 3 are bonding pairs. So now if you have the kit, you find the one there that has the 4 pieces on it, and then if you want to build an NCl3, just whatever color you have, just work with it. You're just going to assume that that's your nitrogen, and then you're going to add on your 3 chlorine atoms. Now, if you want to color code them, the chlorine is labeled as the green ones. And so you basically wind up with a molecule that looks something like this. Now, if we were to determine the polarity of the bonds, what we do is we'd go back to the table of electronegativities. We'd look up the electronegativity of the nitrogen and the chlorine. We see that both of these here have electronegativities equal to 3. Because each one of them is equal to 3, we say that all of the bonds here are nonpolar. All of the bonds are nonpolar. And again, this is because of the fact that the electronegativity of nitrogen is 3.0, electronegativity of chlorine is 3.0 as well. Well, since all of the bonds in here are nonpolar, what we then say is that the molecule itself is nonpolar as well. So this becomes, or is classified as, a nonpolar molecule. If we then want, any questions on this one here? This one's easy. So now we do another one like Cl2. We do something like Cl2. We draw out its Lewis diagram. We could bond a chlorine to a chlorine. We bond a chlorine to a chlorine, which we could show as 2 chlorine atoms like this bonded together. And I'll put them stick together like this to represent it. We then fill in all of the extra dots. Because of course here, if we had calculated the number of valence electrons, we had 2 chlorines each which have 7 valence electrons. There should be 14 altogether. And we build the structure like this. We find out that this bond here is going to be a nonpolar bond. If the bond is nonpolar, and that's the only bonds that are present, then we say that the molecule is a nonpolar molecule as well. So far again, these 2 are easy. And by the way, when you look at these electronegativities, we consider each one separately. So we compare 3.0 to 3.0, then we look at this bond, 3.0 to 3.0, then we look at this bond, 3.0 to 3.0. So even though this nitrogen is bonded to 3 different ones, we don't divide this electronegativity by 3. We simply consider each bond by comparing the electronegativity in each bond that is present. If we go to something like HCl, now I want to draw out the Lewis structure for HCl. HCl would have 1 valence electron for the hydrogen, 7 for the chlorine, for a total of 8. We show the hydrogen bonded to the chlorine. This, of course, uses up 2. Where do we put the remaining 6? On the chlorine, right. Do we worry about completing the octet for the hydrogen? No, we don't. Hydrogen is filled with just 2 valence electrons. So now we go back to our table of electronegativities. We look those electronegativities up. We see the hydrogen sits here at 2.1. Chlorine sits here at 3.0. So again, hydrogen at 2.1. Chlorine at 3.0. Now what we do is we look at this molecule and we want to assign the polarity to them. And to assign the polarity works something like this, because as we defined electronegativity, we said that the electronegativity was a relative measure of the attraction an atom places on shared electrons. We say that the larger the electronegativity, the larger its attraction for those shared electrons. So coming back here, which of these atoms has a greater attraction for shared electrons? The chlorine. So remember now that this property is called electronegativity. And if it has a greater attraction for negatively charged electrons, that means that this chlorine, as a result, is going to be partially negative, relatively speaking, and this hydrogen is going to be partially positive. Now, I don't know how many of you have had calculus or how far, but how many have talked about partial derivatives? Have you gone that far? And partial derivatives, we talk about them in mathematics. Partial amounts represented by the Greek letter delta. This is a lowercase delta. So this is partial positive, partial negative. And so these aren't real charges as in ions being totally positive and totally negative. These are partial charges because these electrons are still shared. It's just that they're not shared equally. Because they're not shared equally, those electrons spend more time with the chlorine than they do with the hydrogen. And again, if those electrons spend more time with the chlorine, those electrons are negatively charged, that means this chlorine is going to have a partial negative charge as a result. Yes?
In chapter 4, when they were talking about solubility in aqueous solutions, they were talking about how the hydrogen has a partial positive and the oxygen a partial negative.
Yes.
That's why the ions dissociate, or that's why they bond. Is that what they're talking about here?
It's very similar, exactly. Now, we don't talk about solubility in this chapter here, even though I'm going to demonstrate some on solubility as to why we know this stuff or why we need to know this stuff. But that's more discussed in your textbook in chapters 11 and 12 when it talks about solubilities. And it could be something that shows up on your ACS exam because there are some components of chapter 11 that are on there. Okay, but it is the fact that these partial negatives, because opposites attract, partial negatives are always going to be attracted to something else that is positively charged. And anything that is partially positive is going to be attracted to something else that is negatively charged or has partial negative charges. But now, in terms of polarity, if we wanted to show this, and now we're still dealing with some very easy molecules or examples to look at. If we now wanted to look at this molecule, here's what we do is we use a plane. And so if we want to use a plane to separate it, if we get all the partial positive atoms on one side of the molecule, the partial negative atoms on the other side of the molecule, then we have a molecule that is polar. So again, all the partial positives have to be on one side, all the partial negatives have to be on the other side. And again, this is what makes this molecule a polar molecule. Now, another way that you might look at polarity is this. You might look at it as kind of like being a tug of war. And if you're looking at a tug of war, I don't know, do they even do that in elementary school anymore? Tug of war?
They did when I was there.
Yeah. It might be one of those things that's too rough for kids these days. Somebody might get hurt, right? Okay. But another way that you could do it is you could draw in vectors. And when you draw in a vector, basically we're going to draw in an arrow. And then you're going to put a plus sign on one side. And you're always going to have the vectors point in the direction of the more electronegative atom. And if you can wind up with a net direction, like this that have a net direction to the right, then we could say that this is a polar molecule. So if the vectors don't cancel each other out, then if you can find a net direction, then chances are you're going to have a molecule that is polar. Okay, let's look at another example. Let's look at something like carbon dioxide. Carbon dioxide. So carbon dioxide, if we were to build its model, would look something like this. And I think this is one of them that we built on last Thursday. So if we go back to our notes from Thursday, right here, we did carbon dioxide. We found that CO2 is going to be a linear molecule. So we want to make sure that we show the correct shape of carbon dioxide. When we show its shape here as linear, we then go ahead and look up those electronegativity values. The electronegativity of carbon sits at 2.5. Oxygen sits at 3.5. So again, carbon sits at 2.5, oxygen at 3.5. So now we start assigning partial positives and partial negatives. Which one or ones get labeled partially negative? Oxygen. Again, the one that has the greatest electronegativity is all, and think of the term, electronegative. It's going to be partial negative. And that means that the carbon is going to be labeled partially positive. So now, if we were to think about this, again, this is linear. If you're using the models, you could show this as being linear, and this is your oxygen that's in the center. And then if you were to look at the atoms that are on each side, our criteria now basically says that what we try to do, again, think of this as the carbon, these as oxygens, we try to take a plane and we try to get all the partial positives on one side, the partial negatives on the other. Can we get all the partial positives on one side, the partial negatives on the other in this? Is there any way to do that? There isn't. And since there's no way to do that, even though these bonds are going to be polar bonds, the molecule itself, we say, is going to be a non-polar molecule. And again, it's going to be non-polar simply because the partial negative poles are on opposite sides of the molecule. Now, another way of showing this is to draw along each bond the vectors, and the vectors will point in the direction of the more electronegative atom. And the little cross that's on there, this is by the partially positive atom. So if you want to do it this way, what you can do is you can show a vector going out this way and a vector going out this way. But now, again, if you think of this as being a tug-of-war type of thing, what effect are they going to have to each other? They're going to cancel each other out, because this one here is pulling with like a force of 3.5. This one here is pulling with a force of about 3.5. And again, their effect, since they're pulling in opposite directions, will have the effect of canceling each other out. If they cancel each other out, then, again, we say that the molecule is nonpolar. And if it's nonpolar, another term that we have for that is we say that they have a zero dipole moment. So if it's nonpolar, that means that they have no poles. A dipole is another name for a polar molecule. A dipole and a polar molecule are the same thing. And so if it has a zero dipole moment, that means that we can't even look at poles because they have the effect of canceling each other out in the molecule. Then we look at NH3 as an example. NH3. And I think NH3 was another one that we built here in our last class. If we go back to the last class, check out our models. Now, if you want to build the NH3, this would be a good one to look at. There it is. So let's go ahead and build this one right now. If you look at the NH3, you'll see that there's how many pairs are on the central atom? There's 4. And so again, if we build it, we'll show the nitrogen going down to the hydrogen here. We have kind of a wedge out to the hydrogen. We have a dotted line back to the hydrogen back here, and the lone pair. So now, if we were to build that molecule, we want to make an NH3, we'll take our nitrogen, which has the 4 pairs of electrons, we put the hydrogen on there, and so it's going to look something like this right here. We now want to determine if this molecule is polar or nonpolar. So what we're going to do then is we look up the electronegativities. Electronegativities of nitrogen. How much? 3.0. Hydrogen sits at 2.1. So again, nitrogen sits at 3.0. Hydrogen sits at 2.1. Now if we draw in vectors, imagine us drawing in vectors, and the vectors we want to draw in are all going to point to the atom that is more electronegative. So if we start putting in these arrows right here, we'll draw in one arrow here, and one here. What effect is that going to have on the polarity? Do they cancel out or do they not? They don't. What is the net direction we would find here? The net direction is going to be an upward direction. Now the components that are in this plane, they are going to cancel out because they're all pointing into the center, so anything that's in this plane is going to cancel out. But they all have a net upward direction, so the polarity in this one is going to be pointed in the upward direction. So if you were to show it here, you have your partially negative nitrogen here, your partially positive hydrogens down below. And again, the criteria is if you can use a plane. Well, we can use a plane because it should be very obvious here that these hydrogens are on one plane, and we can separate it with the plane here, putting this nitrogen on a different one. And if we can get them, use a plane to separate all the partially positives on one side, the partially negative ones on the other, then you have a molecule that is polar. So again, this one here is going to be a polar molecule. And again, if you're looking at it in terms of vectors, you'd see that the vectors pretty much all point in this direction here, and they are going to have a net direction that is in that upward direction towards the nitrogen. Any questions on that piece? Any questions? Okay, now one of the reasons why we spend time with this is that there is a general solubility rule that says likes dissolve likes. Likes dissolve likes. And what this general solubility rule means is this. It means that substances comprised of polar molecules tend to dissolve other substances comprised of polar molecules. Substances comprised of nonpolar molecules tend to dissolve other substances comprised of nonpolar molecules. So the two substances I have up here some hexane and I have some water. So I have some hexane and some water. So let's look at them, hexane and water. Water is H2O, hexane is C6H14. Go ahead and write out the Lewis diagram for each one of these, and then determine their polarity. Determine whether these molecules are polar or nonpolar. Determine whether they're polar or nonpolar. So I'll give you about 2 or 3 minutes. Once again, draw them out. While you're doing that, I'm going to get this stuff ready for a demo up here. if this works for me anymore. But fine. Well, it will work for me. It's just I don't know if I got my hair out enough so it will work. All right. Well, let's go ahead and check the shapes. Water. What type of shape does this have? Bent. Is this a polar or non-polar molecule? Polar. That's because oxygen has an electronegativity of 3.5. Hydrogen sits at 2.1. The partially positive atoms are hydrogen. The partially negative would be the oxygen. Can we use a plane to separate the partial positives from the partial negatives? Yes, we can. In fact, this one here we can see like right across here. We get the partially negative oxygen on one side, the partially positive hydrogens on the other. How about the hexane? What do we do with the 6 carbons? Carbon chain, right. How many carbons in that chain? 6. And then what do we do around the carbons? Add in the hydrogens. Now, actually, if you see a shape like this, you don't even need to look up electronegativities. Is this polar or non-polar? Non-polar. Because even if the electronegativities are the same, then it would definitely be non-polar. If carbon and hydrogen have a different one, there's no way to get all the hydrogens on one side and the carbons on the other. So this is going to be non-polar. So now, let's look at, I have these 2 liquids in these burettes, and I am going to take this balloon, there we go, and these are balloons, by the way. They're not anything else. I forget when I grab these balloons that they look like something else. Okay. Okay. So now what I'm going to do here is I'm going to take this balloon and rub it in my hair, and I am going to bring it up next to the burettes, and we're going to see what happens when we do it and see if we can guess which one is which. Here's the first one, and we see that nothing's happening in this one. So I'll move it over by the next one. That's this one over here. So I'll bring this over here a bit. There we go. I guess I should have started right there in the first place. Now watch what happens when I bring the balloon up to this liquid. Do you notice what's happening? It's being attracted. So now the question is, which one of these here is water? First one here, or the second one? Second one is, right. And that's because when I build up an electrostatic charge, water is comprised of polar molecules, and those polar molecules are going to have an attraction to electrostatic field. So now this is one of those demos that I call my kitchen chemistry demos. If I were to all of a sudden now come back over here and put this up next to the water, we'll try the stream here. Can you see that liquid? There you go. We'll try to get a nice stream of liquid out of here. And now if I put this over here, the balloon next to it, you should be able to see how the liquid is attracted to the balloon. And it has to do with the fact that the balloon is building up an electrostatic charge, and it has attraction for the polar molecules that is found in the water. So now, since we know that one is polar and one is non-polar, what should happen if we mix these two together? Here's the hexane, here's the water. What should happen now if I shake this up? Will the hexane dissolve in the water or should it not? Should not. So shake it up here. And then you should see that the two layers wind up separating back into the two individual layers itself. And so, let's see if I can put this on here and you can see that. You should be able to see the two distinct layers in there. So now if I take something like iodine, whoops, this isn't iodine, this one here is iodine. Is iodine, which is I2 polar or nonpolar? Nonpolar. So I2 is nonpolar. Which layer should it go into?
Hexane.
So go into the hexane. And the hexane now has a density of about 0.7 grams per milliliter. Water is 1.0 grams per milliliter. So hexane is which layer? One on the top. So if I put the iodine into here and shake this up and stop this, what we should see is that the iodine does in fact go into the hexane layer, because again, lights dissolve lights. So it's just a very quick way when we talk about why should we care about polarity. This is one of the reasons. Now, the why you should care probably isn't going to be as apparent until you get into your second semester. We start talking about solubilities and then try dissolving things. I mean, you talked about solubilities a little bit when you did your precipitation reactions and such, but it's going to have a much bigger role to play when you start talking about solubilities and solutions in more detail in your second semester of this course. So any questions on the demo? Question?
Does this explain why oil and water don't mix according to popular?
It explains 100% why oil and water doesn't mix, because if water is polar, that must mean that oil is nonpolar. 100% explanation. Anybody else? Okay, now it's not always as clear as polar and nonpolar. You'll have some stuff like alcohols which have a mixed polarity, and there's and soaps have a mixed polarity. For example, if you get grease on your hands, like I work on my car and on my equipment a lot, get grease on my hands. Well, I go and wash it with water. What's going to happen if I try to wash it with water? Yeah, it runs right off. So if you want to get the grease off your hands, what are you going to do? You soap it up. And it turns out when you learn about soaps in the second semester, soaps have a portion of the molecule that is ionic, which dissolves into water, and they have a portion that is nonpolar, which dissolves into the grease and the oil. And the two then wind up pulling each other out, and you wind up getting the grease off of your hands. So again, there's ways that they work like that, where the polarity then plays a very important role. All right. We're going to wrap up here the course for the semester by talking about orbital hybridization. Orbital hybridization. Now, if we were to look at molecules, let's say that we looked at something like H2O as an example. And we've already talked about the structure of H2O. If we were to draw out a water molecule, we talked about the bond angle in here the other day. The bond angle in H2O is how much?
92.
It's not 90, it is 105. And of course, you didn't have to memorize the 105. You had to learn that it was less than
109.
109.5. But I'm telling you here now that it's 105 degrees. Now, if we were to look at the, I guess this would be the orbital diagrams and the electron configuration, we could start by looking at the central atom. We want to talk about what happens to these electrons in this central atom. So we're going to start by looking at the electron configuration for oxygen. So we're going to look at an oxygen atom and say, what is its configuration? So if we wrote out that configuration, I know this is a review, but let's see if we can do that here for oxygen. We find oxygen right here, which means its configuration is going to end with P4. And if we wrote out a complete configuration for oxygen, we would write it as 1s2 to count for these two here. Then we do these two, which would be 2s2, and these here, which would be 2p4. So it'd be 1s2, 2s2, 2p4. If we then looked at an orbital diagram of oxygen, an orbital diagram for an oxygen atom would look something like this. We would say that it has the 1s subshell, has the 2s subshell, and has the 2p subshell. And we start putting in electrons. The 1s is going to have in there 2 of them, and their spins will be opposed. How will the 2s look? Full, 1 up, 1 down. And then when we get to the 2p, how does the 2p subshell look? Up, 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 and 1 down. Looking something like this. So now it looks like we have 2 of these 2p subshells that are half filled. And because they're half filled, then we could say, oh, well, not a problem here. We're going to have hydrogen come in. We'll have 2 hydrogens. Each hydrogen is going to contribute 1 electron to these, and will form a bond. And then our 2 lone pairs are going to be right here. So these could wind up looking at, now don't write this down yet. These here are going to be the lone pairs. These here would wind up being your bonding pairs. Now again, don't write it down yet. I'll tell you when you can. So if we use this argument here, we go back to our p orbitals. And we'll remember the way that these p's look. And when we look at them, we have their orientations, one where it lies along the x-axis, one that lies along the y-axis, and one that lies along the z-axis. Now, how do we describe these angles relative to each other? They're 90 degrees. This is 90 degrees to this one, and it's also 90 degrees to this one. This is 90 degrees to each of these 2, and this is 90 degrees to each of these 2 here. So if what we're saying then is that we have these half-filled orbitals and they sit at 90 degrees to each other, one might expect that if they're half-filled orbitals, we now imagine these overlapping with each other, that we would expect to find a bond angle of 90 degrees. We don't find them at 90 degrees. What we find them at is about 105 degrees. And so if you think back to what we did here the other day, we were taking these sticks. We started actually with balloons, and we said that those balloons represented these electron pairs in 3-dimensional space. When we placed them into 3 dimensions, we found that in 3-dimensional space we can't get 4 pairs of electrons any further apart than this right here. And we described this as being the shape of a tetrahedron. Okay, and so this is a tetrahedral shape. So now, in the tetrahedral shape, these angles wound up being 109.5 degrees. And that's more in line with what we observed for the H2O as being 105 than there being 90 degrees. So what happens is this. And so I'm going to erase this now. We can't explain it using these because the bond angles aren't right. So what has to happen is these must go away, and instead what happens is that these orbitals right here, I'll put this on a different color, these orbitals here go through a process of hybridization. And now you can start writing if you want to write. We would say that these orbitals now are going to hybridize to yield 4 orbitals of equivalent energy. 4 orbitals of equivalent energy. Now, if you think of what hybridize means in biology or genetics, what does it mean if you hybridize something? A hybrid takes on traits of both pairs. Okay? So the same is true when it comes to orbitals. When these hybridize, it takes on some traits of each pair. And so if you remember the shapes of the orbitals look something like this. We have s orbitals, which have the shape of a sphere, and we have p orbitals, which have the shape of a dumbbell. And so what happens then is that these will wind up forming 4 orbitals, all of which have the same shape, and those orbitals have a shape something like this. It's kind of like a small lobe and then one large lobe. So again, this is what an orbital looks like when they hybridize. So it's kind of large, like it has a single piece like this, but it still has 2 lobes, which are like the p orbitals. So we actually wind up with 4 orbitals that have an equivalent shape. Now if you look at these, they look a whole lot like those balloons we were tying together the other day, don't they? Okay? And so this is basically like the big piece of the balloon with the little piece that's tied on the end. And so if all of a sudden now you start tying 4 of these together, and remember that the electron pairs are in here, then they start repelling each other, and in 3-dimensional space they wind up taking on this type of shape. And so that's exactly what a hybrid orbital looks like. And these here are called sp3 hybrid orbitals. They're called sp3 hybrid orbitals. And to get the label sp3, here's where this comes from. An sp3 hybrid orbital comes from the fact that we've used one s orbital and 3 different p orbitals to make it. So all together then we can have a total of 4 of these sp3 hybrid orbitals. So the way that it looks like then is this. We could look at what the oxygen looks like. We could say that we want to look at the orbital diagram of oxygen in H2O. And if we want to look at the orbital diagram of oxygen in H2O, we would then show it like this. We would say that we have the 1s sublevel, and then now we are going to have 1, 2, 3, 4 sp3 hybrid orbitals. Orbitals. Okay, now notice how I grouped all 4 of these together. And they should all be the same size. Let me go back and just change this here. They should all be the same size. Okay? Well, now it looks too small, but all right, they're all the same size. And notice now that up there we had 1 by itself, and then we had the 3 p's. So now with hybrid orbitals, we show them collectively. And now if we want to show what happens, the 1s doesn't change. The 1s stays the same. But now, if we want to show what happens in oxygen, we're going to show 1. Remember now, oxygen has how many valence electrons? It has 6. So we put in 1, 2, 3, 4, 5, 6. Just like this. And now, these 2 pairs represent the lone pairs. And then if we want to show the bonding pairs, we'll show them with the hydrogen. So I'm showing it here with a different color. These here represent the ones that come from the hydrogen atom. And these here are from the hydrogen. So these here represent the 2 bonding pairs. These here represent the 2 lone pairs. And again, in 3-dimensional space, they all have equivalent energy to each other. And that's why all the bond angles wind up being the same. All these angles wind up being 109.5 degrees. Though in case, again, in water, again, the 1 pair is held more closely to the central atom, so that actually causes some repulsions to kind of push those bond angles a bit together. Any questions on this one? Okay, then let's look at something like SF4. SF4. And I think SF4 is another one that we did here the other day. Let's go back and check it. I'm trying to use ones that we've used already. So here it is, SF4. Let's go ahead and take this structure that we drew the other day. And I'm going to see if I can copy this and paste it. So we will copy, which is this one here. And then I'm going to come back and paste it in for today. There we go. So we have a structure that looks something like this. And in looking at the structure, we'll see that we have how many lone pairs? One. And how many bonding pairs? 4. So all together around the sulfur we have how many pairs altogether? 5 pairs. Now of course this is one that exceeds the octet rule, and we said before we were going to revisit this, and now is the time we're revisiting. We want to explain how in the world sulfur can exceed the octet rule. So to do that, we're going to start by looking at a sulfur atom and look at its electron configuration. So we come back to sulfur. We see that sulfur is located right here. So in the square brackets we're going to put neon. After neon we'd put in 3s2 and 3p4. So again we'd put in neon, followed by 3s2 and 3p4. The next thing we're going to do is we're going to look at the orbital diagram of a sulfur atom, just like we did for oxygen before. So to look at its orbital diagram, we're going to put the neon in square brackets. And then we're going to show the 3s subshell, and then we'll show the 3p, looking something like this. And we put them in. We put in 1, 2. And in the 3p, we'd put in how many more? 4. So how should these 4 go? 1 down. Now as we look at this, it appears as if we only have room for 2 more electrons in the sulfur. But clearly this isn't the case. We're showing the sulfur with a total of 5 groups around it. Well, it turns out that in the D subshell we also have, or in the third energy level, we also have the D subshell. And these are empty right here. And so even though we don't have any electrons in them, they still exist. So now to explain what happens here with this, we need to ask ourselves again, how many groups, how many electron groups are there around the sulfur? How many electron groups are there? 5. There's 5. Now, this is how you're going to tell how hybridization occurs. Count the total number of electron groups around there. The last one, when we counted H2O, we counted a total of how many groups around the oxygen? There's 4. In this case now, there's a total of 5. And the total number of electron groups will tell us how many orbitals need to hybridize. So if we have 5 groups around a central atom, that means we're going to hybridize a total of 5 orbitals. If we only have 3 groups around a central atom, we're only going to hybridize 3 orbitals. If there are 6 groups around the central atom, then we're going to hybridize a total of 6 groups. So count up the total number of electron groups. That tells us how many we need to hybridize. So in this case here, we need to hybridize how many? 5 of them. Well, we start with 1, 2, 3, 4, and the 5th one's going to come from the D. So what we're going to do then is this. We are going to say that we are going to hybridize these orbitals right here. these will hybridize to yield 5 orbitals of equivalent energy. And again, we get the 5 orbitals simply because of the fact that we have 5 groups around the central atom. That's how we decided on this number 5. And so that means we have to select 5 orbitals. We only have 4 of them in the S and P, so that means we need to use 1 here from the Ds. Now the names of these hybrid orbitals, what are these going to be called? We used how many S's? 1 of them. How many P's did we use? And how many D's did we use? 1. So these are going to be called sp3d hybrid orbitals. And again, they're called sp3d hybrid orbitals because we use 1 S, we use 3 P's, and we use 1 D orbital to make it. So then what we do is we go ahead and write out the sulfur atom in, so we're going to look at the orbital diagram. I can't spell today. Orbital diagram of sulfur in SF4. And to look at the orbital diagram of sulfur in SF4, basically we have the neon like we did before, the neon core. We have the 3s subshell. No, we don't. That's hybridized, so that's not even available there. So it's basically going to be 1, 2, 3, 4, 5. These are going to be the sp3d hybrid orbitals. These are going to be the sp3d hybrid orbitals. So now we then go back and ask ourselves, how many valence electrons did the sulfur have? It has 6 valence electrons. So now we put in those 6 valence electrons into here. We put in 1, 2, 3, 4, 5, and the 6th one goes right here. 6th one goes right here. And of course that must mean that this pair of electrons represents the lone pair. And so then if we want to represent the ones that come from the fluorine, we'll say that this here represents the one from the fluorine atom. We can then put in 1, 2, 3, 4 into here to represent the 4 bonding pairs. So we have the 1 lone pair, we have the 4 bonding pairs in 3-dimensional space. It winds up looking something like this. We add on the fluorine atoms, we put them in 1, 2, 3, 4. And again, we have the lone pair that sits here. And again, in terms of our geometry, we'd say that this one represents the shape that is the seesaw shape. And again, we have the lone pair that sits out here. Blah, blah, blah. There we go. Any questions on this? Okay, now, summary of all this stuff is right here. This is linked to your D2L content for last Thursday. I'm going to, if it's not there, I'll link it for today. This summarizes basically everything that we've looked at in Chapter 10. So if you know the electron pair arrangement, if you know that the electron pair arrangement is linear, then that tells us that there's 2 electron groups. The hybrid orbitals are going to be sp hybrid orbitals. Tells us there's 2 bonding groups, 2 lone pairs. Again, the molecular geometry is linear. Looks like this example. If we went to something that has 3 groups around a central atom, 3 groups means you need to hybridize how many orbitals altogether? 3. So if you look at it, these hybrid orbitals are called sp2. So of course you don't see the superscript on here, but the superscript that's implied on the S is a superscript of 1. So by looking at this, you should be able to tell that this means that we have 3 hybrid orbitals. If we hybridize 4 orbitals, that's called sp. How many do we need if we have 4 hybrid orbitals? It'd be sp3 right here. So if we have 4 electron groups, then we have sp3 hybrid orbitals. If we have 5 groups, we just looked at that one. It's going to be sp3d. And if we have 6 electron groups, so what do you think that's going to be? sp3d2 hybrid orbitals is what we'll have. So again, simply by looking at the superscripts, this is 2 plus 3 plus the 1 that's implied here gives us a total of 6. So there's a total of 6 sp3d2 hybrid orbitals that are around the central atom. So again, if you want to look at it and all the shapes that are implied, I'll have this linked. I don't think that your textbook puts these all together in a single table. I don't remember if it does or not. But if it does, I have this linked here to D2L, and you can check it. Fun thing about this was my sabbatical project a couple of years back. You can actually look at all these shapes here in 3 dimensions and rotate them around and zoom them in and everything else to look at them. So, any questions on these? All right, then the very last thing we're going to look at today is what we call pi bonds and sigma bonds. Sigma bonds, we'll look first, then pi bonds. All right, here's what a sigma bond is. A sigma bond represents the first bond between 2 atoms. And we say that the overlap is along the axis. Between the 2 atoms. And I apologize for not getting this printed out for you. This has been an insane week here. And then the last piece we'll just save to later. And then we're going to look at pi bonds. And pi bonds, these here represent the second and third bond between 2 atoms. And on this one here, we say that the overlap occurs on opposite sides of the axis between 2 atoms. Now, if you have a molecular model kit, you can build these along with me to kind of check out what their applications are. We're going to build a sample of these 2 molecules. We're going to show one that has a formula of C2H4 Cl2. The other one's going to have a formula of C2 H2 Cl2. And I've built these here, or I should have had them built at some point in my kits. I'm sure I have them there somewhere. I do. And they're close enough to being finished so I can easily make them. So now to look at these, I'm going to show the first one here. This is the C2H4Cl2. This here has only one bond between these 2 atoms. With only one bond between these 2 atoms, the bond that is between these 2 atoms is a bond that we call a sigma bond. So the first, and it kind of sounds like single. So a sigma bond is present in a single bond. And it tells us that the overlap occurs on the axis between the 2 atoms. And so we'll put it back here on a sigma bond. The overlap is on the axis between the 2 atoms. So that means it lies right along the axis. And if we're looking at these 2 right here, that means that the overlap is right along here. So if you imagine these 2 red pieces overlapping each other, if the overlap is right along the axis, If I rotate these around now, notice that that overlap remains intact. So in other words, that overlap is along the axis. That means that that overlap remains intact, and I can spin this around. Okay? So whenever you have only a single bond, which is a sigma bond, that allows for free rotation. And the significance of that is that if these green ones here represent this chlorine, notice that if I write them showing them on the same side, that is the same as showing one up and one down. Because in molecules, atoms are in constant motion, and because they're in constant motion, they can be in any one of these positions at any point in time. Sometimes they can be on the same side, sometimes they can be on opposite sides of each other. Now when we go to a double bond, one of the bonds, the first bond between the two atoms is going to be a sigma bond. The second bond between them is going to be a pi bond. And in a pi bond, the overlap occurs on opposite sides of the axis to each other. So now, you can think of these here, the red overlapping with the red and the yellow overlapping with the yellow. What happens now if I try to rotate these? The overlap no longer exists. That means that the bond has broken. Okay? Well, it turns out that that doesn't happen. Because the overlap is on sides opposite each other, if I turn this, if I try to turn it, that means basically I'm prevented from doing so, because by turning it would imply that the bonds are going to break. And they don't do that. So an example of it would be something like this. Here we have the two chlorine atoms that are locked on the same side. And here we have the overlap occurring on opposite sides. If I try to spin this around, what happens? I can't do it. These chlorines are locked to the sides that are the same as each other. Or if I have this one right here, I could have it where these chlorines are locked to the sides that are opposite of each other. And while these both have a formula of C2H2Cl2, these are not the same chemicals as each other. These are isomers of each other. Isomers have the same chemical formula, but a different structure. So again, these are isomers of each other. And again, isomers have the same chemical formula, but a different structure. The difference between these is something that you're going to pick up on when you start the second semester of this course. The difference between these is that this isomer is what we call a trans isomer, because these are on sides that are opposite of each other, like transatlantic. And this isomer is called a cis isomer, and that's spelled C-I-S, cis. They're on the same side, like sisters. And you'll hear about cis and trans if you hear about things like trans fats. And trans fats, it turns out that the term trans comes about by how atoms are locked in around a double bond in those fat molecules. And trans fats, of course, are the fats that aren't very good. Those are the fats that you'd like to avoid. But again, we can't get into that here. But if you want to know where that comes from and why the sigma and pi is important, that's where that is important. So we come back, we want to kind of finish this thought off right here. The extra bullet points. We could say that this means, if we only have sigma bonds present, this means it allows for rotation along the axis. And in this one here, basically, these do not allow for rotation along the axis. So whenever you have sigma bonds present, rotation is allowed. Whenever you have pi bonds present, that is, when you have double bonds or triple bonds, they are not going to rotate. They are going to be held in the fixed positions because of the overlap that occurs on opposite sides of the axis. So that wraps us up for material. What I will want to say, I know we are going to have a review, and I'll say this again on Thursday, but I know this has been an extraordinarily difficult semester for all of you. I appreciate you allowing me in here to be your teacher. It was, I know, difficult for you. It was difficult for me as well, but I want to appreciate the work that you put in here this semester for me. So thank you so much.